Alright. Hey everybody, we're Body Physics and my name is Luke.
Clara.
I can't hear you! Aye, Captain.
Okay, you guys have to speak louder and clearly. Okay, let's start over.
Hey everybody, I'm Luke and we're Body Physics.
I'm Clara.
I'm Ryan.
I'm Daniela.
Hi, I'm Yui. Alright, so the first thing we learned on day one was presentation skills, and so that first slide was exactly what you don't want to do. So we learned that you have to speak clearly, speak loudly, and you have to have good posture.
So we covered several different things this summer. The first chapter we worked on was the cardiovascular system. We learned about the heart and the lungs and how oxygenated blood circulates throughout the body.
And then after that, we moved on to studying biomechanics, which is basically the study of how the body relates to physics and how the anatomy moves in the world.
And then we moved on into our final project, which was the prostheses and endoskeleton, and we used what we learned in the previous biomechanics chapters and other lectures to help us create a prosthetic using household materials.
We also learned about game design, fetal pacemakers, and as well as joint replacement.
So our class got to get a Skype call from a Cooper alumna. Her name was Jill, and she works at a company called Stryker. And it was interesting to learn about what her role as an engineer in a company. And the first step to engineering is figuring out the user needs, and it's important because the engineer has to make products that fit and match what the user wants in the product.
So after the user needs are the design inputs, and pretty much what the design inputs are the blueprints of the engineering process, and during this process is when they try to figure out ways to meet those user needs, and once those user needs are met, they then can move on to the design process, and the design process is where they begin assembling a prototype.
And once that prototype is created, it goes through a lot of testing, and depending on what works and doesn't work during that testing period, it will go back through the process.
So in our first chapter, we learned about the cardiovascular system, specifically about two types of flow, laminar and turbulent, and also how blood pressure affects the flow of blood in the heart.
So the first hands-on activity that we did as a class was a sheep heart dissection. This was a really good experience because we got to get up close and personal, see the internal anatomy of the heart, and we learned how structure relates to function. Just one more slide. So our first project was to model the cardiovascular system using only household materials. So we had to demonstrate the movement of fluid flow throughout the cardiovascular system, and these prototypes can be displayed during lunch, so you can go take a look at them.
And then we went on to the biomechanics chapter, which is, as Ryan said earlier, is how physics applies to body movement and body mass.
So part of biomechanics is learning how muscles work. So muscles are basically attached to your bones, and they receive electrical signals from your brain to contract, and when they contract, they can move your bones and rotate your body.
So a really big part of biomechanics is physics. In our biomechanics project, we used certain physics concepts like force equals mass times acceleration, and a software called FISMO to track the center of mass of certain subjects in a couple different short video clips. We looked at the position data we received and calculated velocity and acceleration.
So in our final project, we learned about prosthetic and exoskeleton. In this project, we learned how to design and create our own prosthetics, Flash exoskeleton. In our first prototype, we used household material to construct our design.
And for our final project, we all continued our exoskeleton or prosthetic, and we were given a budget, and we were allowed to use advanced techniques such as 3D printing to create this final product.
All right, hi everyone. I'm Clara again.
I'm Shu.
I'm Chloe.
And I'm Eric.
And this is our extend-a-skeleton hand.
So the goal of our project was to create an exoskeleton hand which can be used to manipulate objects from a distance. So previously we had 2 prototypes, and for our final project we decided to utilize various aspects of both prototypes within our final project. So for our project, for the bones, we decided to use laser cutting technology in order to create the bones. We decided to use 3D printing in order to create the joints. Whereas for the thumb, we printed a specific joint in order to show the full range of movements available by the thumb. In addition, we used rubber tubing to act as a counter tension for the muscles. And finally, we decided to use strings and wires to act as the controls for our final project.
While constructing our project, we encountered many problems. The first problem was 3D printing. We realized that 3D printing doesn't work with small pieces, as a 3D printed small piece is very fragile and the size is very inaccurate. As a result, we used metal pin instead of our 3D printed design. The second problem we encountered was tolerance. So when you have a pin and a hole the exact same dimension, the pin cannot fit inside the hole because it is physically impossible. So as a solution, we just use sandpaper to sand down our pins.
All right, our third issue that we encountered was adhesive. We used hot glue for a large part of our project, but hot glue doesn't stick to acrylic surfaces well, and it wasn't adhering our project together properly. So as a solution, we taped on cardboard, which is a rough surface, and was much better with the hot glue, and this helped us attach the different pieces of our project together. And finally, a simple problem we had was that a lot of the pieces we designed were breaking, and this was both due to material and design. So our solution to that was to redesign the pieces or redesign certain parts of our project to allow for larger pieces to fit.
As you can see in the video, we used an arm brace to secure the exoskeleton onto your arm, and a glove that has strings attached to the exoskeleton hand. So when you move your hands, it will mimic the exact same motion, so allow you to manipulate the objects far away. Thank you. Thank you.
Hi everyone, I'm Jenny.
I'm Daniela again.
I'm Luke.
I'm Stella. And together we built a prosthetic arm.
All right. So before we start and showing you guys our prosthetic, there are 2 major muscles in the arm that we decided to replicate. And it's the anterior deltoid, which helps you lift your arm up, and then also the biceps, which helps you bend your arm.
So we initially wanted to make a prosthetic arm that would open up a door. So we created that little cardboard model in the middle to test it out. We realized that it wasn't going to work, so then we just decided to make the arm move up and down and bend. And we modeled the pulley after the cardboard prototype on the side.
We decided to 3D print 2 different shapes for our arm, and the first first shape that we 3D printed was the hand, and it kind of looks like the Lego hands, and it was used to scoop something. And the other one was a pulley that we attached to the motor, so when the motor spun, the pulley would turn as well.
For the first and second day building, we made the arm and we used door hinges for the elbow and shoulder joints. And then we also taped paracord to represent the anterior deltoid and the biceps. And we taped them onto a tire and rotated it to see if it would do the functions of bending and lifting. But we encountered a problem as it would only do the lifting function and not the bending. So we figured out that if we placed the strings on opposite sides of the tire and rotated it clockwise, it would lift the arm up, and counterclockwise, it would bend the arm.
So the next thing we did was attach the claw to the arm. We gave it a back brace so the wrist wouldn't bend too much. Then we got a continuous servo motor that would spin our pulley all the way, and we attached it. But the only problem is the other end of the pulley would bounce around and it would fall off. Yes, as you can see in the red circle.
So on the fourth day of building, we finally connected the circuits to our arm, and when we plugged the circuits to our computer and we programmed it, the motor turned and the arm raised up, and we glued the motor to the arm.
And we learned with any engineering project, there's always problems that you can run into, and definitely with our project, we learned how to problem solve. One thing that we ran into was that the arm itself was very heavy, so we had to add a second motor to fix that. And the axle that the spool was on wasn't flush against the motor, so we fixed that by wiring that up, and then it was good to go.
And this is just some of how our prosthetic looked in the end. And on the right, you can see the anterior deltoid lifting the arm up, and on the left, the bicep doing the bending motion. Thank you.
Hi guys, I'm Mayuri.
I'm Jessica.
I'm Daniel.
And for our project, we built a prosthetic leg. So some of our user needs were for leg amputees, such as war veterans and animals, so they would have the ability to walk and they would be capable of performing daily functions. Some of our design inputs, we wanted to be able to bend and affordable, comfortable, but yet sturdy and easy to move. As you can see in this picture, it's a prosthetic leg bending.
For our design, we found inspiration from our last household prototype. As you can see in the GIF behind me, 2 gears rotate the thigh and a ball and socket joint rotate the foot. For our first prototype, we use a plastic ball for the thigh socket, a wooden plank for the shank and ankle, and ball and socket joints for knee and ankle rotation. For our second prototype, we started off with the thigh, where instead of the plastic bowl, we 3D printed it. We also changed from the ball and socket joint to utilize motors, and connected those motors to the socket using metal dowels.
Okay, so the second part of the second prototype, we decided to we wanted to make a leg, like a shank. So, and the plan was to have a motor underneath the thigh socket, which would then attach itself to the shank, and that would rotate the leg. So initially, we wanted the shank to be made out of wood, because that's a lot more accessible than any other item. And we were planning to put like a hole in the wood, and therefore the motor would then go into the hole, and the motor would go into the hole and rotate the shank. However, we realized that the wood was a little too heavy for the motor to rotate it, so therefore we instead went to start to 3D print the shank, which was a lot lighter and a lot more efficient. Next, we wanted to make the foot. So again, we wanted to rotate the foot. That way, it would be like more like as if you were walking. So we So we added another motor at the bottom of the shank, which will then be attached to the foot. And initially, we wanted the foot to be made out of like a wheel and a wheel on a piece of wood. However, we realized that there are a couple of problems with that. Initially, one problem is that it was a lot harder to connect the motor to the wheel on the foot, as wheel on the wood, and it was also a little too heavy. So instead, we went to a piece of foam, which was a lot lighter and a lot easier to connect the motor to. So in the future, we would like to make sure our prototype would be actually like usable by people. Therefore, it would have to be larger, because again, like this was more of a prototype. It wasn't really able to be used by an actual person. We also hope that in the future it would be able to be manually used rather than just automated, rather than just having like a computer being like controlling it. You'd be able to choose when to bend your knee and everything. And we also hope that you'd have like there'd be more uses, because right now like the only thing you'd be able to do with it would be like to be able to walk normally. However, we hope like in the future you'd be able to like plan to like jump or run even. So that's it. Thank you.
Thank you.
Hi, I'm Noah. I'm Roshan. And I'm Greg. And we created the mechanical ACL knee brace we call the Armadillo. So all three of us here are athletes, and we know that one of the biggest issues in the sports world are ACL tears. The ACL, known as the anterior cruciate ligament, connects from the femur to the tibia, and it can be partially or fully torn when the two twist in opposite directions. So as we designed this knee brace, what we had to keep in mind was that there had to be enough structural support for the knees, but also that it had to be lightweight and compact because we wanted it to be used in-game. It has to be easy to put on or take off for the athlete, so that, yeah. So when we originally designed this, we broke this down into three components. The compression bags, which are the main mechanism to prevent the ACL injury. Those would be used when inflated on each side of the knee, they would compress and prevent the ACL from twisting or partially tearing. Our second component was more for rehabilitational purposes. It was a pulley system that would help the player bend and extend their knee. To make sure that both of these components would function, we had to include sleeve support, one sleeve on the thigh, another one on the shin, to make sure that the airbags or the pulley would not slip up or down.
So the first step of our design process, we were only allowed to use household materials. The compression bags were placed on either side of the knee and were made out of plastic storage packing material, right here. And the two pulley systems were placed on the lower sides of the knee and helped for flexion and extension of the knee. And the thigh and shin sleeves were made out of medical bandage wrap and were reinforced with popsicle sticks. For our advanced prototype or final project, we wanted to fully automate the brace using voltage-induced pumps and sensors and etc. We wanted to make it more lightweight and compact for in-game purposes and make it more custom for the athlete. And we wanted to add an addition of an armadillo-like knee cap armor, hence the name, the Armadillo.
Okay, so we also had to program a lot of like the pumps, the motor, so that the compression bags would inflate. So the first step was using the IMU sensor, which basically gets relative position for whoever's like using it or moving it, and then get the raw data from that, and then get the computer to read that data, and then from there transfer the prompt to make the motor and the pump move by putting it into a microcontroller, in this case an Arduino board, and then from there we make the Arduino board turn the motor or pump air into the compression bags.
So here are two images of the sleeve laid flat on the table. Here's the deflated airbag, which is concealed by the fabric to keep it in place. And here's the CO2 bike pump, which we use to inflate the airbag with the motor. And on the right is the final end result when the airbag's inflated.
All right, so this is basically our Armadillo part of the contraption. So it's basically every single one of these plates are 3D printed, so we had to design it on SolidWorks so that we can print them out, and it replicates the folds of a armadillo's hard shell, and the holes on each side are so that you can move it and extend it, and when you put it on your knee, it moves with your knee, so it allows for flexion and extension, and it's mobile. So basically, our end result is a medical device that we can use that is fully automated, and the data from the IMU triggers whether the compression bags will inflate so that the ACL will not tear and to prevent injury, and it's also comfortable and flexible, and it allows mobility. And basically, the most important part for this project was working through mistakes, because we had a lot of trouble attaching things and programming, etc. So we learned to just work through that and keep going. So thank you.
Thank you very much.
How's it going, everyone? My name is Zadkiel,
I'm Prince.
Renee?
and we have designed a prosthetic leg.
All right, so as stated before, part of the engineering process is the user needs, and for this project, the user needs was to build a prosthetic or exoskeleton limb that would help humans perform everyday tasks.
Our design inputs were that we wanted to make the ankle move by using a ball and socket joint, make the knee rock back and forth by using a 4-bar linkage.
All right, so basically what a 4-bar linkage is 4 different bars of different lengths, and the smallest bar is called a crank, and you use the crank to move rotationally, and on the opposite side is another bar which moves translationally from left to right, as shown in the diagram.
To create our leg, we first designed and 3D printed the foot. Then we created the 4-bar linkage. To do that, we used a laser cutter.
As seen in the pictures, as shown on the screen, this was our 4-bar linkage. However, we did trial and error to find out the exact measurements to be proportional, to not create friction or any. Yeah.
One problem we had with the bars was that it cracked many times, so we fixed the problem by making the bar wider and longer.
And along with it cracking, the wood that was used for the legs, they kept colliding with each other, so to fix that, we just sanded off the edges, and that worked successfully for us.
And there were also mistakes with the holes. They were too small. However, we went back to SolidWorks and we fixed it up with the correct measurements. This is a video of our working prototype. It works successfully, functionally. It's amazing. Thank you, everybody.
Hey, it's Ryan,
Sarah.
Yuri.
And Matt.
Together for our project, we worked on designing and building a prosthetic hand.
In this video, you're going to see what we learned and what we created.
So at first, we actually started with a sketch, a simple sketch that has 3 joints per finger. And then to bring it to life, we used household items like foam and string in order to actually make the prosthetic hand. Then we decided to add a wrist to add lateral and horizontal movement. And it's really interesting. I feel like... And so some challenges with this prototype is that we had trouble mimicking the thumb and palm motion. We also had trouble having a firm grasp on the objects we wanted to hold. And also we wanted to make the process automatic instead of manual because we were just pulling strings to close the fingers.
So for our advanced prototype, we decided to 3D print the fingers. So each finger consists of 3 parts. You have the top piece, and then you have the middle piece, and then you have the bottom piece. And the top piece is rounded like the top of your finger, and the middle and bottom piece assemble right into it, as shown in the picture on the right.
In our original prototype, we used toothpicks as a joint. We changed that up in our next model by using a clip-on feature. This proved unsuccessful as the axles were not concentric and they didn't fit in properly because the plastic was not flexible enough. So we changed that and resorted back to using toothpicks.
And also one final addition that we had for the final prototype is we actually added hinges to the palm to actually give it more agility and more space to move.
And in addition, we added motors to help spool the strings instead of manually pulling them, which helped make it more automated as we wanted to in our advanced prototype.
So as you can see, this is our final product. And on the top right-hand side, you can see our front and back views of the product. And on the bottom left, you can see that we added a box underneath, cardboard, that holds our breadboard and circuits that will spin the string to close the fingers.
Thank you for listening.
Thank you.
Body Physics would like to thank our funding sources and everybody else who helped us with all the projects. Thank you.